We're gonna wrap up some content we did not explain in detail, right? So message passing, we explained in at very high level, but did not go through the details. And then we will explain user interface, and that will be all the content we cover for this semester. Right? So next week we will have maybe review session, and whatever we teach, we talk about in next week won't be in the final exam. Okay. And before that, I think course evaluation. I'm not sure whether it started. I do the course evaluation, and I do want to hear, in particular, in this AI assistant area, what do students want to learn? What do you worry about? Right? So I think as instructors, we ourselves, we do worry. How should we adapt to these tools? I don't think we. So I'm not one of the faculty who think that it should be completely banned. But I do think we need to find a way to make sure it helps students learn instead of kind of on the opposite, right? So because if students rely on these tools too much, they're not really learning, and when it comes to the real world, when you really start building complex systems, it will bite you. These experience when you build this system level software, when you force yourself to really write elegant code, that is also how in the future, even if you use AI assistants, how you will instruct those AI assistants, right? So you need to be able to tell whether they are doing a good job, and you need to give correct instructions. And without learning this yourself, without being able to design and write elegant and complex code base yourself, it will be very hard for you to be able to instruct AI assistants properly when it comes to real world software systems. And yeah, so I do want to hear about students' worries, and what do you think we can adapt, and what do you think in your experience that helped you learn, right? So these AI tools helped you learn instead of preventing you from learning the correct knowledge, right? So if you rely on these tools too much, you really miss the opportunity to learn. Okay, and yeah, so and there are indeed a lot of research already coming out, right, from MIT, Stanford education, who researchers focusing on education. People do find that relying on these AI tools too much will hurt students' ability to write, not just write code, just write in general, and also hurts if you for computer science students, if you rely on AI tools too much, it also hurts your ability to develop realistic software. There are already research probing this, right? So yeah, so we need to figure out a way to fight this together as instructors and students. Okay. All right. Inter-process communication. So we explain this at a high level, right? So the processes that are running concurrently in the operating system need to communicate with each other in order to cooperate. Okay, and that's a process within one OS, and very often a process from one OS need to communicate with a process in another OS. That is also called inter-process communication, but over the network. Okay, yeah. So IPC, this inter-process communication it happens within an OS and also across the network between two machines. Okay. It can be used for exchange data among processes and some forms of process coordination. The general technique is known as message passing. And so you have two processes and they communicate by sending a message to the other process. Okay. And there are also other techniques, shared memory, as two processes can share the same piece of memory directly. Right? And yeah, so, but the more common deployed technique is message passing. So shared memory, if you have a shared memory between two processes, the benefit is that accessing this shared memory is faster than message passing. But the downside is that maintaining that this shared memory is consistent, right, among the two processes is very difficult. Right, so the general technique is message passing, right, more widely deployed. Even for message passing, there are multiple approaches to do it. So the first approach is that message passing is one of the many services the OS offers. Right? So messages are basically data items sent from one process to another, and are independent of both normal I/O and process synchronization services. Okay, so message passing is just one of the many services. Your OS build other services independently, like synchronization and other services. The other approach is that the entire OS is message-based. Okay. The entire OS is message-based. What does this mean? So this is typically called, I'm not sure whether you have read the paper or not, right? This is typically called microkernel. So every component in the OS is a process. Even your file system, your memory management, right? So these components are all managed by a process. And these components communicate among themselves, among each other through message passing. Okay, so this is much rarely implemented. Right? So usually only this microkernel OS use this message-based approach. The entire OS is message-based, and so the components, they do not communicate with each other through function call. Right? They communicate with each other through messages. Okay, so this is actually, let's take a guess. Can you imagine what is the benefit of this? What is the entire motivation after using this approach compared to the other? Okay. Every component is a process, and the components communicate each other through messages. Yes?
Maybe like you could restart like the file system.
Exactly. You can tolerate partial failure. Right? So in Xeno, if your file system crashes, your entire OS is stuck, right? But in this kind of microkernel service, because every component is a process, one of them crashes, you just need to make sure the others are fine or stop there and then restart that one process. Okay, so it's more fine-grained modularization of OS. So each component is a process by itself, and these components communicate with each other through messages instead of function calls. Okay. The downside, message passing is much slower than function call. Right, so this concept of microkernel has been there for starting from 1990s. Right, so it's invented in the 1990s, but it's never made it into mainstream OS. Right, so most of the OS use approach one. So similar to Xeno's approach, right? Just because message passing, right, is much more expensive than function call, and so inside the OS, this is often unacceptable. Okay. There are recent research, right? So I think that that OS from Huawei, I think they built an OS a couple years back. That OS from Huawei utilized this message passing idea more widely in their OS kernel. Right? Their OS kernel is closer to a microkernel, and they have some tricks to overcome the overhead of message passing. So if you're interested, right, you can read these recent research papers. But in general, so message passing is slow, so most of the OS is still designed using the first approach, including ZeBu. Right, so yeah, to understand the issue, we begin with a trivial message passing facility, and we allow a process to send a message directly to another process. In principle, the design should be straightforward, but in practice, many design decisions arise. Right? So in ZeNu, the high-level idea of the message passing is very simple. You have one message slot in every process. If you have read the message passing that component, you really only have one slot. So a process can only send one message at a time. A process can only receive one message at a time. And so other processes will check whether the receiving process is already receiving a message. If it is receiving a message, it will back off and send the message later. It's a very, very simple message passing facility. But we will look into it deeper, right? Because even such a simple message passing facility has a lot of subtleties. Okay. So yeah, so these are some of the examples, questions you need to answer before you decide. Right? So first, message size, you want a fixed or variable size, right? And if it's a variable size, do you want a maximum message size? Right? And how many messages can be outstanding at a given time? Where are the messages stored? Right? And how is the recipient specified? Does the receiver know the sender's identity? Reply supported? Is the interface synchronous or asynchronous? These are all critical decisions that will impact the semantic and the performance of a network facility, a message passing facility. Okay. Synchronous and asynchronous. So this is one of the most important decisions that you make when you design a communication library. A synchronous interface means that the operation will block until the operation is performed. Now, when you send a message, if the message is not sent out, you have to wait there. When you receive a message, if no one is sending the message, then you need to block and wait for that message. Right? That is what synchronous means. Right? Sending process is blocked until the recipient accepts the message being sent. A receiving process is blocked until a message arrives. Right? Easy to understand and use, and a programmer can create actual processes to obtain asynchrony. Right? So this is a simple semantic, and you can create, if you want asynchrony on top of this synchronous interface, you can have your process, right, the user programmer process, create another process to be responsible for communication. In this way, you can achieve asynchrony. Right. So this is just said that you can implement asynchrony on top of synchrony. Right. That's also why ZeNu provides this synchronous interface. Right. So it's the simplest message passing facility, and if you want asynchrony, you can implement asynchronous communication on top of it. An asynchronous interface, the process starts an operation, but it does not need to wait for this operation to finish. Right? So the initial process will fire this operation and go back to continue whatever it's executing. Right? It's kind of fire and forget. Send this, start this operation and just go back to whatever it's doing. And there will be a notification arrive when that operation completes. Right? So it's like an interrupt, right? In OS, interrupt is similar. So you start an IO operation. When that IO operation finishes, you will get an interrupt. Right? So it's also a type of asynchronous operation. Right? So a notification will arrive when the operation completes, and the notification can arrive at any time. There's no guarantee, and so notification entails abnormal control flow, right? So sometimes it's called callback. Right? So when there's a callback, your process need to stop whatever is currently executing and handle that callback. Right? That's why it's called an abnormal control flow. So it's more difficult to understand the use, and pooling can be used to determine the status. Right? Sometimes you keep pooling because you don't know when this asynchronous operation finishes, so you might want to repeatedly check whether it had finished or not, right? If you are really waiting for some event to happen. Okay. So reasons why message passing choices are difficult. Right? So because message passing interacts with scheduling, right? You can imagine that if, especially in a synchronous API, because the process will be blocked on the send and receive operation. Right? The other side, right? When you are sending, you're blocked on the receiving process, whether it's receiving it or not. When you're receiving, you are blocked waiting for the other process, the sender process. If unfortunately the other process scheduler made some poor decision for the other process, you might run into starvation. Okay, let's see a more concrete example. Right? So process A sends a message to process B, and process B does not check the messages. Process C sends a message to process B, and process B eventually checks its messages. And if process C has a higher priority than A, right, the question, should B receive the message from C first? Okay, so A, C both send messages to B, and the message arrived in the first in, first out order, let's suppose. Right? A's message arrived first, C's message arrives later. Right? But the C has a higher priority than A. Right? In this case, which message should be handled first? So this would affect the scheduling environment, whether you will always have the process that has highest priority to be running in your OS. Right? If you handle A's message first, you handle the message from the process that has a lower priority, and you unblock it. Right? So process A will be unblocked and will take over to execute. Right? The process C, which has higher priority, right, so will be delayed by the process A, which has a lower priority. Okay. All right. Message passing affects memory usage, right? If a message is stored with the receiver, sender can use up all the receiver's memory by flooding the receiver with messages. So this decision, where to store the messages, is important. If messages are stored on the sender side, receiver can use up all the sender's memory by not accepting messages. Okay, so this is also possible. Okay. Yeah, so Xenu has a very simple and basic message passing facility, and we'll explain it. Right? So this facility provides direct process-to-process communication. Each process is one word. Right? It's a fixed size, right? Not variable size. One message is stored with the receiving process. Okay? So and the process only has one message buffer. Okay, and the message reception is synchronous and buffered. Message transmission is asynchronous. Okay, the facility includes a reset operation. You can reset the communication channel. Very simple, and let's take a look. So this is the interface. It consists of 3 system calls. I send PID message, which means that your current process wants to send a message to this process with this PID. Okay. And this receive means that the message is going to be waiting, locking, receiving a message. Okay. Receive control, right? This is slightly different from receive. We will take a look at it later. If you understand receive, that's usually sufficient. So send the transmit message to a specified process. Receive blocks until a message arrives. Receive control removes an existing message if one has arrived, but does not block. So yeah, we will look at it later. Okay. Each message is stored in the receiver's process table entry. So the system uses a first message semantic, meaning that the first message sent to a process is stored until it has been received. Right? So this message will be stored in the receiving process until the receiving process calls receive. Right? Subsequent attempt to send to the process will fail, right? Before this receiving process calls receive. That buffer, that message buffer is occupied, and during this period of time, any other process sending to this receiving process will not succeed. Okay. All right. How to use this first message semantic? Right? It's very, very basic. You can imagine that in any of your programming course, you never write a program that are allowed to only send one message to another process. If you have a program in any multi-process application, you need to set up socket and send message to another process. I don't think you ever use this semantic, first message semantics. I think it's always that you assume you can send a continuous sequence of messages to another process. It never happens you use this first message semantic. It's very simple, right? And so to use it, right, how does Xenu still make it useful? Right? It's very limited functionality. How does Xenu still make it useful? Right, so you wait for one of several events to occur, right, so such as IO complete, a user presses key, and data arrive over network, a hardware indicator signals a low battery. Right? These are all interrupts. You wait for this interrupt to happen, and and you use the message passing facility to wait for the first event. Right? Create a process for each event, and when the process detects its event, have it send a message. Right? So how? Why this first message semantic is meaningful, it's useful, because you are creating one process for each event. Right? That's how Xenu makes it useful. Right? To receive a message, or to receive the message for an event, you create a separate process. That's how you make it's really useful using. Otherwise, this functionality is too limited. Okay. All right. So when the process detects an event, it will send a message. So the IDM receiver uses to identify the first event that occurs, right? So it uses to prepare to receive a message, right? This is a receive control. It clears the message buffer, right? And so after it clears the message buffer, this allows other process to send messages, and then it receives a message, right? So this code returns the first message that is sent even if a higher priority process attempts to send later. Okay, it only handles the first message. So after adding this message passing facility, what are the process states? We have the process state diagram, and before and after adding this message passing facility, the process has new states. Okay, so while receiving a message, a process is not executing because it's waiting, it's locked on receiving this message. It's not ready, it's not suspended. Okay, so it's just waiting for the message to finish, to be received. So therefore, the new state is added called receiving, and the state is entered when the receive is called, and the code uses a PR receive to denote a receiving state. So this is the diagram. So in the current execution state, if you're current, when you call receive, you're going into the receiving state, right? And and when another process called send, that will unblock this process who's blocked on receiving and make this process transit into ready. Does it make sense? That send is send from another process. It's receive. The current process called receive. That's what make it into transit into the receiving process. And that send is not this process, right? Because this process blocked on receiving. It's not sending any message. That send is from another process. Another process send message, and this unblocks the current process who's blocked on this receiving, and it will transit to the ready state. So yeah, this is a more detailed explanation. Right? The current process calls receive. Receive checks the current process entry in the process table, and if no process arrived, the receive will move the calling process to the receiving state and block it. Okay, and once a message arrived, right, it's sent by another process. This process is moved to the ready state, and the execution of receive will eventually continue when the schedule choose this process from the ready queue and do context switch. Okay. And the code in receive extracts a copy of the message from the process table entry and resets the process table entry to indicate that no message is present, and then return the message to its caller, receiving one message at a time. Yeah, so how do you do blocking to wait for a message? Right? Receive will find the current process entry in the process table, and then set the state in the process table entry to be a received state instead of a current, indicating the process will be received, and will be receiving, and then it will call rescan to pick another process to schedule in that new process. Okay, this is very simple, right? So the receive is implemented like this, and so it will get the process process entry of the current process and set its process state to be received. Right? Here, PR receive is to change the current process's state, and then we'll call reset. Okay. When the magic happens on the sender side. When another process sends a message, it will check whether the receiving process, right, is doing this, is receiving, trying to receive a message, and we'll see on the other side, on the sender side. Okay. So to send a message, a process called send, specifying the destination process and message to be sent to that process, and so it returns an error if the process has already a message waiting to be received. Okay. If not, it will deposit the message and make the process ready if it's in the receiving state. And this is what changes the previous process who's already scheduled out. Okay. Changes to be ready state. So this is a send. This is just some regular checks. Okay. And let me see. And this is the PID. This is a receiver process's PID. And then you use this PID. Let me see. One second. Yeah, I think we lost some code here. Probably need to look into the Zeno code here. Right? But this is this part. This PRPTR should be the process entries pointer for the receiving process. You should use the PID to get this PRPTR of the receiving process, and then that's why when you assign the message to the receiving process's buffer, that is how you deliver the message. Okay. I think if you look into Zeno's source code, you should see it. But in this slide, probably we missed that part of the code. This is the receiving process. Okay. Right. So you check whether its state is in receiving, and if it's in receiving, you make it ready. Okay, this is how you unblock a process that has been previously blocked on receive. Right. The sender process will change this receiver process state to be ready. Okay, and remember this ready function internally it calls reset. The ready function internally calls reset. So the process will change it to be ready, put it in the ready list, and call reset if needed. Okay. Receive control. It clears incoming message and return a message if there's one waiting. We won't go into too much detail about this. It's essentially clearing the message buffer. Okay. Okay. So that is I think that is a missing part. We explained message passing at very high level, but did not go into the detail. Right? User interface. Right? We were about the user interface, which is the final component of OS that we haven't covered. Right? And last lecture we talked about the high level. Right? So there are different types of user interfaces: graphical user interface, command line user interface, and so we'll dive into more detail today. A quick recap, right? So each OS provides two types of interfaces. Right? The first interface is for applications, which is application program interface, and it is usually a set of system calls that are allowed to be used by the applications. And when you write programs, you use these system calls. Okay. The other interface is for human. Right? So it's an interactive user interface. It can be command line interface or graphical user interface. Okay. We explain all of these. Okay. So what is a command line user interface? We already explained this. Right? It is a big loop. Every loop iteration is going to take wait in the console, right, to prompt the user to input a command. Block waiting for the user to input the command. And once the command from the user is there, it will execute that command. And after it finishes executing this command, it will give the user feedback, right, the results, and then wait for the user to execute to input the next command. And that is a command line interface. A big loop just waiting for user to give it commands. Okay? We explained two type of implementation, and we mentioned that the command line interpreter right now nowadays usually is implemented as an application that is separate from the OS. Right? So the first type is the command line interface is implemented inside the OS. The second is that it's implemented as an application. And this is how it's done today. Right. So this is an example, right? So the Unix shell, it runs as a standard application process and provides a per-line processing, right? Every time you input a command, you press enter, right? A new line, create a new line. That's when you indicate to the command line interpreter that you have finished giving it a command. Okay, and it interprets each line as a command, using the same syntax for scripts as for interactive input. And that's why in your when you write bash scripts, you use the same semantic, the same syntax as you are typing in your command line. Okay. It also offers basic programming language constructs, right? You can define variables. You can write a sequence of statements instead of just one statement, and you can have a definite and indefinite iteration, right? You can write loops, and you can have a conditional execution, right? All of these exist in the shell scripts. Right. Share variables. Right. So I'm not sure how many people have used share variables. Right. So this is the basic. Right. So if how to define a variable, you give it a variable name and you use an assignment and give it a value on the right side. And when you use echo, you can use this $sign to indicate that this is a variable. Right? You're referencing a variable, and this echo will print out the value of this variable. Okay. And it produces a line of output containing the word hello. Yeah, so giving this above, this command gcc$x.c, right, it will compile the file hello.c, right? This gcc hello.c. That's essentially what it does. Right? So more complicated example, right? Suppose the current directory contains multiple files, A, B, C, right? And yeah, what does the following line mean if typed into a shell? Yeah, we already, I think these comments already explained it. Right? So you define a variable, and this is the value of the variable, right? And you do ls dash l using this variable b star, right? And this will list the file bbb, right? Because ls command will do regular expression matching and using this b star, pattern matching of using this b star, and the pattern will match bbb file. Okay, and the touch bb creates another file that starts with b, and if you use ls dash l with this pattern again, right, it will list both bb and the bbb, these two files, right, because this pattern matches both of them. All right. Let me see. Okay, yeah, I think this binding time, right? So this let's skip the binding time for now. Right? This variable binding itself is a more complicated concept. Let's skip variable binding for now. Okay, maybe we won't be able to skip it. That's all right. So this is yeah. I kind of forget that this lecture. I mean, if you really want to understand every detail of this slide, it's more like a small programming language course. Right? So you learn about variable binding. You learn about syntax, lexical analysis, syntax analysis. So this slide is like explaining a language design of a shell language. So there are a lot of details in this slide that will take an entire class to explain very clearly. So I'm not sure whether you guys have taken the programming language course in this at Purdue. Yes.
We have taken, we did take a course, computer architecture, where we covered, or one of the projects was building a shell. So we learned a bit about lexical analysis.
Okay, that's good, yeah. Okay, cool, yeah, we'll go through it, we'll still go through it. Right? But if you want to know more about the details, I'm not sure whether people are still interested in because programming language design is very interesting, but also old-fashioned. Right? So if you are interested in language design, right, you want to take a compiler course and a programming language course, at least these two. Right? And the compiler tells you, teaches you how to compile a high-level language into intermediate language and then machine code. And programming language design teaches you how do you design the high-level language. Right? So there are different ways to design a high-level language and different features that we have. And this is very programming language design is one of the most important topics in computer science history, and many Turing Award winners, right, they want their this topic itself, right, programming language, produced a lot of Turing Award winners, and it is one of the most important topic in computer science. But because of AI, it's becoming less attractive to many students, right? Because now you can communicate with computer using natural language. Why do you want to learn about a computer language, right? So, but to myself, right? So, programming language design is very interesting, right? Compiler and programming language, and if you're interested, right, you should definitely look into it. In this lecture, we'll just go through the high-level design of a shell language, and it actually covers a lot of topics that you will need to learn in a programming language course. But if you want to know about the detail, the real concept and the theory behind them, you should take a programming language course. Okay. All right. So the basic Unix shell evaluation algorithm, right? The shell repeats the following steps: read and parse the next command, dividing it into tokens. Right? It performs macro substitution, replace this $x with the value of string x, and evaluating the file name if globing. Yeah, I don't remember what this means. Right. It perform another file name matching, such as b star, and it will perform this variable assignment. Right. So then this variable using the string, and it will search for the user path for the command named by the first token, and invoke the command passing the remaining tokens as argument. So I think this is what they mean by late evaluation, right? So in the very beginning, you do not evaluate the entire thing, and only after you really execute the command, that's when you evaluate the value of this variable x. Okay. So the shell only supports one data type, which is string, and you have built-in commands handle iterations, like while and for, and you have a conditional execution if then else. And you can use quote to prevent a substitution, right, and delay the binding. Right? And single quotes inhibit interpretation within the string, and double quotes allow variable substitution within the string. Okay, and each command is executed by a separate process, and a command pipeline connects the output from one process to the input of the other. Right? So we have already explained that pipeline. In the previous lecture, we mentioned that pipeline is a temporary file device that you create that you can use to bridge the input of a command to the output of a command to the input of another. Okay. All right. Okay. So the shell will act like a compiler. It will compound statements, this while, for, if, and else. That can span multiple lines of input. A long pipeline can span multiple lines as well. Right? So this is what you often see in a shell script. Right? A shell must also handle file redirection. Right? It must check for the consequences. It must check for balance limiters. Right? So this kind of a yeah. So sometimes if will become this kind of weird character that you check for. Okay, so output from a command can be converted into a string, and the content of a file can be assigned to a string. Right? So cat file, it can be assigned to a string. The content of variable can be converted into a command input. Right? You can echo these variables value and use it as a command. Okay. And the literal text can be converted into command inputs. Right? So you can use this literal text and use it as command input to a command. But these are all the syntax that teaches you how to use shell. I think the most useful material for this kind of language like shell scripts and other language is that learn X in 1 minute. If you have, I'm not sure whether people have used that website. It's called Learn X in 1 minute, and it has a list of languages with examples, right? So if every language has just one web page, and if you go through that single page for that language, you should already have a grasp the language syntax lifestyle. So if you are interested, you can visit the Learn X in 1 minute website and go through the syntax for shell language. The shell maintains a search path. The path specifies a list of directories. The shell uses the path during command lookup. I think this is one important thing that I want to point out. So sometimes in your shell script configuration setup, you want to change the path environment variable to add some path. Right? I'm not sure whether people, I think probably people have done that. Right? So add a path, add some path to your path environment variable. Right? And that is because the shell will search for files in the directories that are specified by the path variable, right, by default. You are able to execute a lot of commands directly. When you are using your shell, you can execute ls, you can execute the cat directly, not because this command exists in the directory where you are using these commands. It is because this ls, cat, this command exists in some completely different directory than your current directory that you are working in. Right? But because the path to these commands, to these programs, ls and cat, is encoded in the path environment variable. That's why shell knows where to look for these programs. Okay, so that's why often when you install a new program, a new library, you sometimes need to change the path variable to include the path to this newly installed program. So to find a file to execute, the shell searches the path one directory at a time. Right? It prepends the next directory to the command name and checks to see whether the result is a file. It stops if the file exists. Right? So if you have multiple paths, and in each path you have you installed maybe 2 versions of the same program in multiple paths. And only the first one will be used because the search stops at the first file that matches the file you specify. Okay. Once the file has been found, the shell checks whether the file is executable, and the current directory works like any other directory name in the past. Okay. So the current directory is included by default. There are 2 forms of path banding. Late banding was used in the original shell. The shell searches directory along the path each time a user enters a command. And the early banding, when it started, the shell searches the path and caches the name of the files in each directory. When you start up the system, you do the search and cache the name of files. And then when the user enters a command, the shell directly searches the cache to find whether there's the command that matches the file name. Okay. Yeah, so late binding and early binding have their own efficiency. I think right now it's usually early binding. Rehash. Yes, we won't cover these details. IO redirection. A user can redirect the input or output. The shell provides a separate redirection for standard input, standard output, and standard error. These are three standard devices that you also see in Xenu. Right? Xenu also has these three devices: standard input, standard output, and standard error. And the syntax of IO redirection is using this symbol to, this is redirecting output to a file. This is using this file's content as input. Right? And the syntax for standard error redirection depends on the shell. Another example usage is that background processing. Right? So the shell can create a process to execute command. The shell always creates process to execute command, but you can put the execution of this process in the background. Right? Background execution allows the shell to continue processing concurrently. The syntax is using this symbol. Right? If you add this symbol, I'm not sure how many people have used it, but probably some of you have. Right? If you add this symbol to your shell command, the execution of the command will put in the background, and you will be able to continue to input another command. Right. Pipeline, the output from one process is fed to the input of another, and arbitrary pipeline is allowed, and the pipe between two processes consists of an infinite buffer, and the OS handles process synchronization. Right. So I think we mentioned previously, this pipe is actually very powerful. It's a very powerful concept, and the reason that you have it is because in Unix, everything is a file. The pipe is also a file device. Everything is a byte sequence, and this pipe is not different. It's just a temporary file device that is treated as a sequence of bytes. Shell scripts, right? It's a name given to a file that contains a set of shell commands. The file must be executable. So you essentially composes a list of commands you want to execute and put it in the script. Okay. I assume that people have written this. I won't explain it in detail. Okay, the design principles for command line interface functionality. The interface should be sufficient for all the commands that you want to execute. Orthogonality, there should only be one way to perform a given task. Right? Otherwise, if there are multiple ways to perform a task, it will be very confusing. This is an example, a very interesting feature. In most language design, we want orthogonality, meaning that every keyword, every command is responsible for one feature or one functionality, and the functionality should not overlap between the commands. Do you know there actually exists a language that violates this, right, orthogonality, right? In the design philosophy of that language, it intentionally violates this, and it allows there to exist multiple different ways to achieve the same functionality. Anyone have heard of Perl? Language Perl? Right? So Perl is designed because around this philosophy. Right? Its design philosophy is that it tries to allow humans to take guesses. Right? Even if you do not know the internal of the language, and it tries to say that, okay, you can take guesses, and very often humans' guess can hit one of the functionality that it provides. So it provides different ways to express a search, for example. It provides different ways to perform LS and search. Right? For each functionality, it provides different ways to do it. And the goal is that it tries to make sure that even the human does not know the exact way to do it, the human might be able to guess how to do it. But it causes a lot of confusion. Right? So when you use Perl, it's at least with my experience using Perl, it's quite confusing. All right. Consistency, right? Commands should follow a consistent pattern, and at least astonishment, a user should be able to predict the results. So these are all good principles to design language, not just the command interface, right? But for all language. Okay. Yeah. So design and implement of the Xenu shell. I don't think we will go into the detail of the Xenu shell. So we won't have it. We won't cover it in the final exam, right? So this is just for you to understand how an example user interface can be implemented for an OS. Okay. It only illustrates the basics of a shell, right? So Xenu shell is again a very simple shell. It has a fixed set of commands compiled into the shell itself. Interprets each line to be a pipeline of one or more commands, right? And each command follows a familiar command syntax, right? One command is a command name and a list of arguments. Right? The first command may specify input redirection, and the last command may specify output redirection and background execution. The notation x star means 0 or more x, right? And this means that x is optional. So X shell, the Xenu shell is written ad hoc, right? So the data structures and algorithms are very unusual. The idea is just to show a minimal implementation of a shell and illustrate the shell organization without unnecessary complexity. So so I think as what is admitted, right? So if you want to learn how to implement a shell properly, Xenu might not be the best example. Right? It just illustrates the minimal example of a working shell. Okay. Let me see. I'm not sure whether we want to go through these details. Okay. So the syntax, I don't think we want to go through the detailed syntax, but we'll go through the pipeline. Right? So a shell is organized like a one-line compiler with two main parts. So it has a lexical analyzer that divides the input line into a series of tokens. Right? Each token is a word, and stores each token along with the type of the token. Okay. And then a parser checks to ensure the sequence of tokens is valid. Right? It turns the token into a command with arguments and then executes the command. Okay, this is a very typical pipeline of a compiler. Right? If you have taken the compiler course, this is the shell is a very small compiler. Right? So because Xenu shell only handles one line at a time, the shell reads the entire line and calls a lexical analyzer to divide the line into tokens. And then the lexical analyzer eliminates the white space, right, blanks and gaps, and checks for invalid tokens, right, and returns the number of tokens found, right, and each token with their types. So you have so this is an unusual. So I don't think we want to go through the detail of the unusual design of Xenu. Right? So I think that you just need to understand at a high level. Right? So there are two stages: lexical analysis and the parser. Yeah. So we don't. So because this is unusual, right? So what you really want, right? If you want to learn about shell, you want to take a look at a more standard shell implementation. Right? So don't be affected by the unusual implementation of Xenu. Okay, parsing. Right. So the lexical analyzer divides the entire input line into tokens before the parser runs, and the parser uses occurrences of the pipe symbol to divide the lines into segments that each consists of a command with arguments. and then handles each segment independently. This is also a lot of detail, which we won't go into the detail, right? So essentially, the parser will identify the command in each line and the arguments in each line, and then it will execute the command with the proper arguments. Okay. So Linux only passes 2 arguments to a command. Right? So one is integer count, how many arguments there are. The second argument is an array of pointers into argument strings. Right? So one count the number of arguments, and second is an array. Right? So this allows the command to use arbitrary number of arguments. Okay. The first argument is a command name. Yeah, so this is an example. You have 3 arguments, and the second one is this array that stores all the arguments to your command. All right, so command execution. All right, once the lexical and parser their execution finishes, you will invoke a command, and each command is executed by a separate child process. The shell creates a process to run the command. And the first process in the pipeline can have the input redirect to a file, and the last one can have the output redirect to a file. So this input should be redirected from a file. Right? So the first process can read the input from a file, and the last command can output its content, its output result to a file. Okay. And process in the middle of the pipeline receive input from a pipeline and send its output to a pipe. Okay. Yeah, implementation of lexical analyzer. Again, I don't think we will go through the detail of these. If you are interested in this lexical analysis and parser, I highly suggest that take a program language course, a compiler course, and a program language course. They are quite interesting. This is a complete code for the shell implementation, right? Okay. All right. Yeah. I think that's it. Right, so for the shell, I don't think we need to go into detail. The exam won't cover the detail of shell. Right? So the reason we cover shell is mainly to make sure that you have a complete understanding of every component of OS. Shell is the application level, right? So the facing users. This is the interface that you can, the simplest interface that a human can use to interact with the computer. Right? So if you're interested in how to implement the shell, I think the shell is really one of the simplest compiler. Right? So if you're interested in such kind of techniques, take the compiler course and program language course. Okay. All right. Let's see. Yeah, I think that's it for today. We'll end early. Next week is the dead week, so we won't have new lecture content, but we will do some reviews.